Okay, let's get started. So in today's class, I'll start the class with a bit of discussion on assignment 2, and then you have your normal days back and you got Shannon back in the second half of the lecture. So let's talk about assignment 2. Before that, let's do a bit of a logic test. Look at the question on the screen. What's the answer? Yeah? Bob, very good. Many of you have been thinking, keep reading and thinking, well, Alan's on Bob's left, Bob's on Colin's left, and so on and so forth. Then Emily must be on Alan's right. Not really. All that we really need is just this sentence, right? If Alan's on Bob's left, Bob must be on Alan's right. That's all that you need. Now, it turns out ChatGPT is making the same mistake as you are. If we copy and paste that question into ChatGPT, don't fail me. And it gets Emily. Can you guys see it? Yeah. So also makes the same mistake. Now, yeah? Really? That's really weird. Somehow it got fixed. Let's bring up the test.
Video for reading.
So you can actually check it, right? But actually what happens, last time I did it, it actually gave me Emily as the first answer. Somehow now it becomes a bit smarter. So that actually shows something. There's a bit of randomness in the output of ChatGPT. And essentially, even though it shows you a lot of these reasoning steps, but what's really happened behind the scene is that ChatGPT is just making the best guess given some of the input. And the guess is to guess the next word or next piece of information. It's not, well, you can think of it as a little bit of logic reasoning and all that, but ultimately there's a statistical model behind the scene that generates an output based on the context, and the context here being your input. But how does that generation of the output based on the input work? In assignment 2, you're going to try that process. So let's look at assignment 2. We'll start from the beginning. The announcement of assignment 2 just came out last night. A few important things to note. It's going to be due in 2 weeks' time, Tuesday, 27th of May. Due time is actually 4 p.m. this time. We don't want you to sort of keep working until the midnight. Just finish in the afternoon, take a drink, and have a good sleep. There's also a couple of different things from the assignment 1. So in assignment 2, you will just work on your own machine, own coding environment. This time we bring out the test. Last time we kind of be very cozy and created a coding environment, a module on it. This time you have to do it on your own. And to help clarify a bit of the marking, we give you a detailed marking rubric this time, which we'll come back to it probably at the end of this the first half of the lecture. And also, this time there won't be grace period, so don't expect that at the last day you suddenly got another 3 days. Not like that. Due day is due day. You won't have more time. So to get access to the assignment, you go to LMS site, go to assignment module, and then A2. And then in here, you got a link that contains the whole package. And if you download it, here's what you got. If you download it, it's a zip file. If you unpack it, here's what you got. You got a HTML file. This is marking rubric. You got a assignment spec, a PDF, and then there's a skeleton code called program.c. You should write and submit all your code in this single file called program.c for the assignment. And then there's 2 sample test cases that comes with the assignment as well. Assignment submission will be done if you click on, actually there's a link here. If I refresh it, hopefully it will show. there's a button here. If you click on this, it links to a Gradescope site where you can upload your program just like in assignment 1. So far, so good about the general thing about assignment 2. It's just general logistic, nothing about the task yet. So next, let's look at the task. So we're talking about, like, in this assignment, we're trying to understand how ChatGPT works. There's a lot of complex, large mathematical models, machine learning models behind the scene. That's not our concern. We'll look at actually the final bit. If ChatGPT has worked out all those most likely things to be output, or work out the probabilities of different things to be output, Emily or Bob have different probabilities. How does they make the final decision whether it should be Emily or Bob? And that's what we're going to look at in this assignment. Now, you can assume that we have a ChatGPT to work out the probability of these different things to be output already. All that you need to do is to compose those things together based on the probabilities. So here, in this assignment, the output has the input of every test case has 3 sections. First section is just a simple integer that tells you what are the different things ChatGPT can output. This is what we call the vocabulary. So in here, we got 20 words, assuming that we have trained a really silly ChatGPT, maybe using a model of 100 years ago. We train a model that can only generate these 20 words. And each of these words has a probability to be outputted. How do we got these probabilities? Well, we say ChatGPT has this large model, right? But in reality, if you think about the good old days where we don't have ChatGPT yet, how we get this probability? What we can do is we can collect a large collection of text. In my days when I was about your age, I actually did something like this. A very simple model. What we did is we collect 10 years of Wall Street Journal and we count the word frequency in that Wall Street Journal. And then we got the frequency of different words. And based on those different words, we can generate text. And your first task is actually based on this. Our first task would be, given these words of different frequency, let's generate a sentence of, in here, we ask you to generate a sentence of 10 words. Could be 10, 20, doesn't really matter. And all that you need to do is just sort the words based on the frequency, and you generate the words based on the highest frequency to the lowest, the top 10 ones. Now, obviously, it's not going to generate a really sort of sensible sentence, because you probably can guess. In English language sentences, you do a bit of counting. Words like the, to, and is going to be the more frequent ones. But if you put them together, it doesn't really make that much of a sense. So that's task 1. And in the later stages, we will make progressively build a more and more sensible sentence. In the end, get to what ChatGPT can output nowadays. That's task 1. So far, so good. Basically, just word frequency and sort the words and output them. Now, in this words kind of vocabulary, there's 2 special words, start and end. All the other words, they are just English, contains only English letters, except for the first 2. And this is always the first 2 words in the input. They have a special kind of angle bracket to encode them called end and start. These special words indicates the start of a sentence and the end of a sentence. You can think of it, if you got this start, this is what we call a special token. If you got this special start token, it indicates that the next word is actually the real start of a sentence. When we write sentences, we never really write like angle bracket start and then we start a sentence, right? We never do that. But we got that indication of the start of a sentence by capitalizing the first word. In our assignment, we don't consider uppercase or lowercase letters. So you can think of it just like, let's capitalize the next word right after start. Right? That indicates the start of the sentence. And similarly, the special token end here indicates the end of a sentence. You can think of it like as if it's a period, because we don't have punctuations in these words. So far, so good. That's our vocabulary. Now next, it's just a large chunk of numbers. What does this large chunk of numbers mean? This large chunk of numbers indicates if I've seen a word in a sentence, what are the chances of that I'm going to see in the next word? So for example, if you look at a sentence in here that says the answer is to life, world, universe, and everything is. So when I see is, what's going to be the most likely next word? Wow, there could be anything, right? Because is a commonly used word in English. But if you constrain that into our own vocabulary, then maybe only a subset of these words can show up after is to make a sensible sentence. So what are the possible words? Well, here, if you go through this, matrix, it tells you that. But exactly what does this mean? Well, this is actually what we call a transition matrix. If you list the list of words, copy that list of words over from the input that I just showed you, like we start with an N, star, A, N, answer. It's a sorted list, by the way. Now, if you also copy this list to the different columns, you basically transpose the words, okay? You do a transpose of the list of words and make it to different columns. Then a row and then an element in this matrix indicates if you see a word in this list, what's the probability of seeing the next word on that column? So to give an example, if you look at this 0.6, what it means is if you've seen a word in a sentence, what's the probability it's going to be seeing dog as the next word? So we have, so 0.6 basically means 60% opportunity that you're going to see a dog. What's the other 40? Well, the other 40 says a life. So that's what we call transition probability to transit from one word to another word. Right. And each row represents the probability of the next words for one word. So taking another example, if you look at an N, so after N, you can have everything. So that's how we got from the sample sentence. And then another 30% N ran. So that could also make out a sentence as well. So that's transition probability. I also recommend you to build up this matrix in an Excel file. This will help you observe and solve the later three stages. So transition probability, and that's all about the input. The second stage is basically just to read the transition probability matrix. And after you read the matrix, we want you to do some output to show that you did have reading the matrix successfully. So what would the output? The output will be, well, given every word, let's figure out what would be the most likely next word. As we just shown, if you see a, if you see or a word the most likely next word is dog, because dog has a 60% probability, right? And the other life is 40%. So 6% is larger, so we output that. And the arrow here indicates this is the most likely next word. It's not about pointer or anything, just the most likely next word. So if you do this, you got the most likely next word for every word in our input vocabulary, except for the N word, because N is also the indicator of the end of sentence. There's no next word, all right? So that's that. So far, so good. Next, transition probability, next word. Now, once you build up this next word, then we can generate a more natural sentence. A way to do it would be just, well, how about we just follow the most likely next word? So if you say, look at here, if you look at this start is the starting point of a sentence. So what would be the most likely next word of start? Apparently it says the is the most likely one. So I'm going to generate a sentence starting with the. And then what would be the most likely word of after the? Well, let's look at the. The is here. Apparently this one is the most likely one, is answer. So the answer, and if you repeat this process, you're going to generate a sentence that looks like, well, not that much better. It looks a little bit better, at least a couple of words that seems to making sense. But then, unfortunately, after this two word, apparently somehow the is also an option of the next word of two, and apparently has a very good chance because the is a very frequent word in many cases. So somehow by statistics, we found that there's also a very good chance of the after two. And once you have a the after two, you end up with a kind of cycle. You say the answer to the answer to the answer to until you hit, well, here we again set the length of sentence to 10 words. So that's not great. Even if we followed always the most likely next word, it's still not generating a really great sentence. What's happening in here is because if every time we try to generate the next word, we always follow the most likely word. This is what we call a greedy solution, right? If we talk about this solution in an algorithmic sense, this is a greedy solution, a local optimum. Just look at the last word and the next word. But what if we look further ahead a little bit? Well, we promise you with an adaptation of the algorithm, this is actually the next step, the step 4, we can actually generate a sentence that is quite natural. But how do we generate a sentence like this? Now, to understand that, we need to actually do a bit of math. Oops. So this is the sentence that we just showed, that we show you to following the most likely next word. This is sentence that we show. And the arrow here again shows the next word. And we're following the next word. And the number in here, 0.4, 0.6, is the probability of going from one word to the next word, right? So this is the probability. Now, given the probability of every 2 words adjacent in the sentence, how do we figure out the overall probability of sentence? Now, your instinct might be just adding it up, right? Yeah? Multiply that. Why multiplication?
Because each one is dependent on the one that came before, whereas addition is isolated.
Very good, very good. So except for I gave you the answer in here, but explanation is perfect. They are dependent from each other. Like the next one depends on the previous one, and the next one after that again depends on the previous one. So overall, the whole probability of the sentence is a multiplication of the whole sequence of probabilities. It's not simple addition. Now, if we are just talking about multiplication, what if we look ahead a bit? Not just the next word. What if we look at the next, and next, until we see the end word? If we do that, actually, if we do this kind of analysis, somehow, assuming that we have magically found out this is the golden sentence we want to generate, and we do a bit of a calculation of the probabilities for these words. Now, some of this, like in here, for example, this is the moment where the stage 3 kind of model mess up. It just look at the word the, which has a higher probability, it just naively decided to go for that. The life here got a slightly lower probability, such that it got kind of ignored. But if you kind of look ahead a bit, there's actually chances where you can accumulating more higher probabilities later on. For example, if you go from life to universe, there's a 0.8 probability. But if you just go from the to answer, it's 0.6. So if you look ahead a little bit more, we can actually kind of revive from a previously lower probability kind of word combination. And if you multiply these probabilities together, we actually got a slightly higher one. Well, not slightly higher, probably almost twice as high as the previous one. Even though these numbers are always small, because you have to multiply all the probabilities many times, and every probability is smaller than 1. So in the end, if you've got a longer sentence, there's a good chance the overall probability is going to be smaller. But it's all relative. These probabilities are all relative. You're not comparing with yourself. You're comparing with other sentences. Every sentence probability is very small. So among the many small ones, you might still be able to stand out. Now, here we kind of hide a bit of the details in the sense that if you've got a really long sentence, what happened then? If you've got a really long sentence, all the probabilities are very small, and the comparison wouldn't be very accurate because we have kind of talked about the doubles, right? They are inaccurate. So to avoid that, there's a bit of details in that we can translate this product calculation into a summation, and to avoid these really small numbers. You can think about how to do that, but this is not going to be covered in this assignment or in this lecture. Next, we're going to try to figure out how do we avoid just falling into this local optimum kind of trap. And this is the algorithm that we're going to ask you to implement in stage 4. Looks very complex, but hopefully this example will help you understand what's going on. So what's going on is, now we start with this sentence start token or word. Now we look at all the next words with a non-zero probability. So this column here, essentially, it's just a reproduce of the first row or second row in here, and for the numbers for the words where there's a non-zero probability, 0.2, 0.1, 0.2, 0.1, 0.4. this is just a copy of that. 0.2, 0.1, 0.2, 0.1, 0.4. Again, this is the word probability, word transition probability. And these are the corresponding next words. Now, what we do next is that, well, the word start itself, we assume that it's a probability of 1. Why is it 1? Well, we can't do 0 because later on we want to do products. If we start with 0, whatever product you calculate, you always end up with 0. So we start with a 1. And then what we do is that, well, you start with a 1, and I know A has a probability of 0.2. So what's the probability of a sentence with start and A? 0.2, right? It's 1 times 0.2. So at the moment, it's silly. This 0.2 here is just a copy of the probability there. But next step, this number is going to change. It's not like always this word probability anymore, right? So we figure out for this, after start token, we have 4 different choices, and each of them has a different probability. Now we don't just go for the top word anymore with the largest probability anymore, but we use top K. For the assignment purpose, we just look at top 2. And somehow I've managed to sort of set those probabilities that even if we just use top 2, we'll be able to generate that sort of a more natural sentence. In reality, usually you don't just look at top 2, you probably look at top 10 or top 20, right? So just look at top 2. So if you look at top 2 now, we have two possible sentences. Well, each of them is just a piece of a sentence yet. So the top one is the second is A. Now you might ask that, well, there's an A and there's everything, both of them has the same probability. In this case, how do we decide? There's a tiebreaker, you go to the assignment spec. It will tell you that how to break ties in this case. Essentially, what we do is just look at the ones with that is being generated first, and we keep that. And in this case, A apparently got generated first because it's earlier in the column. So we have 2 options, and let's look at both. Now, if you look at this one, and if you look at they are following the previous procedure. After there are 2 options, right? We talked about this just a moment ago. After there's 2 possible words, either dog or life. And for dog, it has a 0.6 probability. For life, it's 0.4. Now, following the same procedure as before, we are going to accumulate these probabilities. And by accumulation, I mean multiplication. So we multiply 0.6 with 0.2. I got 0.12. Multiply 0.4 with 0.2, we got 0.008. Now, following the same procedure, looking at there are again also 4 words afterwards that are possible, and each of them has a different probability. And we also calculate the probability of start the answer following this probability on the arrow is 0.4 times 0.6, you got 0.04. Dog, you got 0.4 times 0.2, you got 0.008, and so on and so forth. Now you have in this second word kind of or partial sentence of 4 words or partial sentence of 2 words. Now we have a total of 6 options. Again, I take the top 2. So important to know, it's not like I take one from each of the 2 branches. I put all this together and I take the top 2. So apparently top 1 is this one, the second one is that one. So it's not one from each branch. It's everything together, take the top 2. If you follow the same procedure, for example, up to here, again, everything comes from the same down branch, and the top branch actually finished early in here because these 2 words, these 2 branches are both smaller than has a smaller probability than these 2 branches. So we just keep going from this one. And if you follow this one, you can see we actually now got a partial sentence that says the answer to life universe, and obviously this is not completed, and you can complete the rest if you spend a bit more time. So far, so good. That's stage 4, and this is how it's got generated. And you might think that this is silly, but in reality, this is actually an algorithm being used commonly in text generation algorithms. Because if you think about it, there are actually just so many combinations. In here, even with this top K kind of solution, we are not thoroughly exploring all probabilities, right? We are still throwing away some of the branches. But actually, these branches, if I wanted to, I can also set up some sort of probability that makes them to generate a natural sentence afterwards if you follow them. It's just that if we follow all these probabilities, follow all the possible words, the output space is just so huge that it cannot be explored in kind of real time. And that's also one of the reasons why, a very small fractional reason why ChatGPT just spit out the words so slowly, because its vocabulary is huge and you need to explore such a huge space. Obviously, there's another large portion of time is being used to calculate the probabilities. Here, it's just that we got the probabilities. How do we produce the sentence? And even just producing the sentence itself is a huge challenge, right? So far, so good. Hopefully, after finishing this assignment, you can go home and tell your parents that I did spend my tuition fee worthy. I did learn something. All right, that's the assignment. So what else do we have in this assignment package? We have a skeleton code. Let's look at the skeleton code. Hopefully, I'm not showing you the sample solution. Skeleton code is somewhat similar to assignment 1. We created kind of an empty main function for you to fill in, and you also fill in the stage functions. You got a lot of this kind of extra kind of coding here about linked list. We want you to try to use linked list in this assignment. Where do we use linked list? Well, when you generate a sentence, you will never know when to stop. Except for we tell you that you can stop by 10 words, but there's also a probability where you stop after you hit the end word, because some of the words actually lead to the end token, and that could be prematurely before the 10 words. So we want you to practice using linked list a little bit, and once you can stop, you don't keep generating all the 10 words. That's that. And the test cases, this is just a reproducing from the assignment spec. And we also give you the sample output. There's a second test case where the output will be programming is fun and algorithms are fun. So you can actually generate two sensible sentences following the two different procedures. So if you just follow the most likely word, you can generate C programming is fun, and if you explore a bit more, you found that algorithms even more fun. Okay, so that's the two test cases. Now, how do you compile and run the program? Well, you compile it and run the program using a compilation command that we gave you, a really long thing, but you don't need to remember it because it's part of the assignment spec. If you go to this bit, it gives you a compilation command. If you just copy and paste that into your terminal, you can do the compilation, and you can run your program. To run a program, we use input redirection to fit the data input data into a program. You say test0.txt, and the scattering code doesn't do much. At the moment, it just print out the stage headers. No actual calculation logic in there yet. But you can keep filling in the code, and once you finish them all, your code should be able to produce what we gave you in the sample test output. Now, once you achieve that state, it's time to submit, and we say that we submit in a gray scope. And after you actually submit your code, here's what you're going to see. There's the usual compilation kind of stuff. Beyond that, it has like compilation command, the C-check thing that you've seen from assignment 1 as well. And in here, it says there's no authorship declaration. To complete the assignment, we ask you to fill in this bit to say your name and student ID for automatic recognition. There are other things that it can check. Here, my skeleton code managed to sort of get away from all those checks, but once you've changed your code, you might actually hit more issues in your coding style, and C-check might give you more issues in here. And then if you give you the test output, this is my program output, it will compare this program's output with the kind of standard expected output. And if we give you that, like for the first stage, it will give you a breakdown in each stage whether you got it right or wrong. And apparently, because my program at the moment, skeleton code is not really generating any real output, so it keeps saying that all the stages there's some error in there. But beyond that, pretty much similar to assignment 1 in terms of the setup and submission. So far, so good. Great. So then leave us the last bit, which is the marking rubric. Let's quickly go over the marking rubric before passing it back to Shannon. So this is the marking rubric file that comes together with the assignment package. There are 4 sections of marking. The first one, or the last one, is the simplest to look at, which is just the program execution. All that we do is we are going to use 2 hidden test cases that you're not going to be able to see while you're submitting your assignment. You only see sample test cases. After that, after the submission deadline, we're going to test it with 2 hidden cases, and we'll check for each stage of the 2 hidden cases whether your program get it correct or not. And each kind of stage output correctness comes with a little bit of mark allocation. By the way, even though here it looks like there's a lot of marks, these marks, they are kind of cumulative. So it's like, it's not like if you finish stage 4, you got 11 marks, and then stage 3, you got another 9 marks. It's not like that. It's more like if you got only stage 1 done, you got 3 points. If you got up to stage 2, you got up to 6 marks. So it's accumulative, not adding them together, all right? So overall, it's just 20 points for the assignment. And then there's structure and approach. A few things to look at. Some of them are quite intuitive, others might be more complex, and I'm going to show you a little bit of example. Duplicate code segments. This basically asks you to write functions. If you see places where your code needs to be repeated, then maybe it's an opportunity to create a function and just reuse that piece of function. Global variables is bad. Try not to use it. Insufficient use of functions. We created quite a few of functions already, but we want you to also create your own functions. And we kind of make it very mechanical. We say that you have to create at least your 2 functions of your own at a minimum. And then for the functions, they shouldn't take a lot of parameters. In assignment 1, we are kind of okay with that. In assignment 2, we are not as flexible, because now in assignment 2, you know how to use structs. And if you really need to pass a lot of things into a function call, think about using a struct to put the things together in a package and passing the whole package, right? That will help you reduce the number of parameters that you need to pass into a function call. Functions too long. I think this is also imposed in assignment 1. You shouldn't write functions that are very long because it's very difficult to read. You have to, again, this is all about encouraging you to break down functions into smaller functions, and then which will help people or other coders read your code, or even yourself to come back and read your code a bit easier and to debug it. Overly complex algorithmic approach. This is kind of a little bit of subjective. Give an example. For example, if you want to find the word with the largest probability or transition probability, you probably can do it in a simple linear scan to find out which one has the largest transition probability, and that's it, right? But somehow, if you decided to use 2 for loops or even 3 for loops, putting them all together somehow to go through the whole transition matrix, then that doesn't seem to be very sensible to me. And that's overly complex approach. Unnecessary duplication, copying of data. This is basically saying that, well, unless there's a really absolute requirement, just keep passing the arrays or some sort of variables around into different functions. Don't just create a copy and pass into a function, create another copy, pass into another function. No point to do that. And the next section, next 3 things about structs. Again, now we introduce how to use structs. You are asked to use them in assignment 2. Equal for equal double testing, that's just dangerous, and you should not use it anyway. Stage 3, we ask you to try to use linked list, and if you don't use that, it's going to be a bit of deduction in there. Stage 4, so all of these are about coding. Stage 4, we also ask you to do a bit of complexity analysis to analyze that really complex algorithm in stage 4. What would be the running time of it? So far, so good about this section. Program presentation, this is about really coding style. The last session is about your approach. Shouldn't be too complex and all mixed up together. Create functions, use structs. Coding style, about like, for example, lines of code shouldn't be too long. Here, 100 characters per line is the limit. Other things, try to avoid using constants without defining them. For example, even in my in my statement code, we gave you a few constants already. One of them is the vocabulary size. By the way, this is the maximum number of words that your program needs to be able to process. We set a limit because to kind of simplify the assignment. In reality, this vocabulary size could be, well, probably wouldn't be million, but easily get to hundreds of thousands different words. If you want to define these constants, define them using uppercase, just as I showed. Vocabulary size is all uppercase letters. If you write functions, you have to have function prototypes. What functional prototypes mean? These are the function prototypes. Choice of function names give names a bit of sense. Well, this is probably not a great example. Stage 1, what does that mean? But at least we have some example that are more sensible. Make empty lists, like create a list that's empty, nothing in there, right? So don't call a function called function A, function B. That doesn't work. Similarly, variables, you don't want to create variables, say variable A, variable B. Not great, right? Create variables that has some meanings. Excessive commenting, you don't have to comment every line of code. That's a kind of thing. On the other hand, you don't also want to be like insufficient commenting. So it's kind of like we ask you to not do too much and not too few. What do you mean by too much? Avoid commenting every line of code. What do you mean by too few or too little? It means that at least every function you created, you have to explain what that function does. That's the minimum. Obviously, if you have a function that's a bit long, a bit complex, you want to throw in a few more comments to explain what they do. Inconsistent bracket placement. Well, myself takes this style of opening bracket at the end, closing bracket at the front. But there's another commonly used style where we also put the opening bracket at the front. You can choose either style, or you can even use another style. But you just choose one style and use it consistently in your code. Don't mix them together. Yes?
In assignment 1, there's a C checker.
Yeah.
Very much prefers this style. So is that something that will be used for this assignment? And if so, if it tells us we have to do it this way, should we ignore that if we're willing to do it another way?
Well, we just show you that we actually submitted this code to Grayscroll, and it can actually pass the C-check thing. It doesn't complain. So this style will also work. And if you want, you can also do the other style, or maybe you can come up with another style. The main thing is don't mix them together. As long as there's consistency, we are happy with it. But also try not to use a really weird one. Like if you're opening here and somehow you end up in there, that doesn't help people read your code. So that's weird, right? So don't do that. Similarly, there's an indentation style here. Also be consistent. If you go for what do you mean by inconsistent? Well, both of them belongs to the same function, same layer of the logic, but one got one tab, the other got like 4 or 5 tabs. That's inconsistent indentation. It's not great. A lot of things, it's common sense. How people read and understand your code easier, or even just for yourself to maintain your code in the future. Right? And lack of white space. And again, common sense. You don't want to put everything all together, right? You want to separate them, like for different functions, maybe put a blank line, dropping a blank line to separate 2 different functions to help people read that. Oh, actually, those are 2 different functions. I should not read them together. That's just that. Lines don't go too long, and that's about it. One more thing about academic integrity, we always promote kind of academic integrity. Is really one of the most important things you should learn. One of the most important things that university values as our own graduates. That you want to sort of. Here we are not saying that you can't even discuss the assignment with your friend. We also want a collaborative kind of environment that you can study with your buddy, right? That's okay. But when it comes to once you can talk and you can draw and all you want, but once you start typing, it needs to be your own code, and you should never look at others' screen that shows their code or show your screen to others that shows your code. We run sophisticated tools to test every pair of submission, and if we found highly similar submissions, we will take actions. So it's always difficult to do those kind of conversation. So let's try not to put me or put yourself in those kind of difficult situation. With that, that's done with assignment 2. Yes?
Instead, using linked list and not the linked list code provided, if
Yeah.
you want to modify the linked list code that's provided in this code,
That's what we ask you to do. Yeah, you should modify the code, and you might be asking because you see this item, right? Not using this provided. This doesn't mean you can't modify the code. We encourage you to modify code, and that's actually the part of the challenge. This is only means sometimes, well, this has happened in the past. Students use ghostwriters. They don't want to use our linked list. They just use whatever linked list package that they're used to, those ghostwriters. They come back with a solution that looks really weird. We don't want that to happen. Right? Anything else? Okay, with that, I kind of use like 15 minutes more than I should, but hopefully Shannon can still survive the second half of the lecture.